All right, so in this video, we're going to be looking at the periodic table, including the development, the way it's set up, and the way we can use it to understand different properties and characteristics of the elements in the periodic table. And when we're looking at the periodic table, the way it's set up is so that the elements in the same group, so going up and down, are going to have very similar chemical properties, whereas the elements in the same row, so going horizontally, won't necessarily have the same properties. But with it, when we're looking at the elements in a group, when we're talking about similar properties, we're thinking about chemical properties, so things like reactivity and things, rather than the physical properties, which aren't necessarily going to be the same or similar, I should say. But the original periodic table was developed, typically Dmitry Mendeleev is credited with it. So he was a Russian or Siberian scientist in the mid 1800s. And what he did was ultimately take data for all of the known elements at that time, and the properties of those elements as well. And he noticed that the patterns within those properties start to kind of repeat. And then he grouped those elements in the same group. So again, the column going up and down. When they did have those similar properties. And ultimately what that allowed him to do was actually predict the properties of elements that had yet to be discovered at that point. So Mendeleev is typically considered to be the father of the periodic table. His version of it, not quite the same as the version that we use today, but it was more or less like the starting point. It wasn't drastically different, but it had the same general concepts there, which is, again, having the similar properties in the same group. And that's why it's referred to as the periodic table, because those properties repeat periodically, what's known as periodicity. And we see those properties repeat on that sort of set schedule. And that's why if we look at, for instance, the halogens in group 17, fluorine, chlorine, bromine, iodine, all going to be very similar chemically. And that's why we have them in the same group. Whereas if we move one group further to the right, now neon, argon, krypton, xenon, helium, even at the top, those are all going to be the same, similar to each other, but those groups 17 and 18 are going to be very different from one another. But the elements in one specific group are going to be similar to each other. And then with this periodic table, the color coding is just related to when those elements were first discovered. And then with this periodic table, you can see we've got some blank spots here, and we're actually just leaving off two of the boxes here. These are going to be some of the man-made elements, so the elements that are produced in laboratories. And depending on the periodic table you see, they may or may not be included in there, depending on when that periodic table was developed. So like this one doesn't actually include any of them. And even with those periodic tables, sometimes they will just have like UUO as the symbol, rather than having the name for that actual element, because in some cases it takes a while for the element to actually be named. So sometimes they just use those as a placeholder related to the atomic number. But with those elements, we're not really going to be focused on them too much in this course. But like I said, Mendeleev, when he was, actually I should go back. So in addition to Mendeleev, there was Lothar Meyer, who at about the same time and independently, so they weren't working together at all, but they were working on the same type of project, came up with a similar periodic table, but for whatever reason, Dmitry Mendeleev is the one that gained more notoriety for it. But like I said, Mendeleev was able to use the properties he was observing to group those elements in the same columns. But occasionally there was just an element that had yet to be discovered. So he kind of just left an open spot there. So if we look at what he has here, he was actually able to predict the properties of germanium. So if we go back to the periodic table quick, germanium is in group 14 here, so below silicon, above tin. When he was developing the periodic table, this had yet to be discovered, and the same thing actually with gallium. He was able to predict the properties of gallium as well. But he noticed that there was this empty spot in the periodic table. He knew the properties of that group. So based on the way he set up the periodic table, based on the properties repeating periodically, he had a pretty good guess of what that element was going to be like. And again, This is on the right-hand side, the actual properties of germanium. And then what he called it was ecosilicon, just because it's one spot below silicon on the periodic table. But you can see his predictions on the left versus what germanium actually is on the right-hand side. So he made these predictions 15 years before the element had actually been discovered, and he was doing it based solely on the periodic table that he himself developed. But because he knew there was that missing spot, he was able to basically predict what that element was going to be like. He wasn't able to discover it, but he was able to predict how it would behave. So if we look at just some of the properties here, so the atomic weight, atomic mass, 72, really 72.59. Density, specific heat, pretty much spot on with all of those. And then with the formula of the oxide, formula of the chloride, what we're looking at is just the ratio in which those are going to combine. So when we look at germanium, 1 germanium for every 2 oxygen, or 1 germanium for every 4 chlorine. That's the exact same thing he predicted here. He just has X as sort of the unknown symbol at that point. And then even if you look at the other ones, the density of that oxide, the boiling point of the chloride, even if he wasn't spot on with some of these, he was pretty close, and especially when you consider he was doing this for an element that had yet to be discovered. So because of his understanding of the periodic table that he developed, that his understanding of that periodicity within those properties, that's why he was able to pretty successfully predict the properties of germanium. And again, he was able to do something similar with gallium, one spot to the left. And the reason he was able to do that is if we look at the periodic table again, it's below silicon, but it's going to be between zinc and arsenic. So that's why he was able to, and then again, gallium similarly, it's just going to be below aluminum, because he knew kind of the properties he was seeing, and then he saw the atomic mass increasing as we go to the right. That's why he was able to predict all of those properties ultimately. And then with the periodic table, we can use it to identify trends within these elements. So some things we're going to look at include the size of these atoms, and in some cases, the size of the ion. So if we gain or lose electrons as well. The ionization energy, which is essentially going to be the energy needed to remove an electron from an atom. And then the electron affinity, which is related to how strongly it's similar to the ionization energy, but in this case, it's essentially how strongly the electron's bound to that atom. Before we get to that, so we can get a better understanding of it, we want to think about what's known as effective nuclear charge. And essentially what this tells us is those valence electrons, the electrons in the outermost shell, what kind of attraction, or how strong is that attraction to the nucleus, and what it's based on. If we look at neon here, is it's based on the number of protons in that nucleus minus all of the core electrons. So if we think about neon, it's got an electron configuration of 1s2, 2s2, 2p, 2p6, 11. Oh, duh. I was wondering why it was 11. I knew that was wrong. So this is not for neon. This is going to be for sodium. They were using the neon core here to represent the electron configuration. Confused myself with my own notes for a second. But if we're looking at sodium, that's why we've got 11 protons. This has got an atomic number of 11. So when we're looking at the effective nuclear charge of sodium, what we're going to be doing is looking at the number of protons in that nucleus. So again, just whatever that atomic number is. And then we're going to be subtracting all of the core electrons, which are going to be everything that's not in that valence shell. So when we think about sodium, the electron configuration, 1s2, 2s2, 2p6, 3s1. So everything but that 3s1 electron is going to be a core electron. So that's why when we look at the effective nuclear charge of something like sodium, we've got an effective nuclear charge of +1. But then if we move over one group to magnesium, Now we've got a 12th proton in that nucleus, but the core electrons are still the same, because now in this case we've just added an extra valence electron, so we've added a 12th electron on the valence shell, or well, I guess a second electron on the valence shell to give us 12 total, to balance out that 12th proton in the nucleus. But now if we think about magnesium, the effective nuclear charge, essentially how strong is that attraction between the nucleus and those outermost electrons? Now what we're going to see is the effective nuclear charge is going to be +2, because again, we've got 12 protons in the nucleus. We're subtracting the 10 core electrons, which leaves us +2 in this case. And then basically, as we move through the periodic table, as we move to the right-hand side, group 13, we're going to see something similar. It's going to be +3, +4 for the carbon family, +5 for nitrogen, 6 for oxygen, 7 for fluorine ultimately. And this is going to help us understand why the nucleus, or why the size of these atoms is actually going to decrease as we go across the periodic table. So this is the formula there for for actually calculating the effective nuclear charge. We use the Z as the symbol for the effective nuclear charge there. And then we've got the atomic number minus the screening constant, which is just going to be the number of those inner electrons, so everything that's not on that valence shell. So again, with something like sodium here, the reason we have 10 is because the valence shell only has that single electron, so all of the other 10 are going to be considered the core electrons there. And as this effective nuclear charge increases, that just means we're going to have a stronger attraction between the nucleus and those outermost electrons. And then when we're looking at the size of an atom, if we're looking at a single atom, what the atomic radius in that case would be is the distance from the nucleus all the way out to that valence shell. When we're looking at the atomic radius between two bonded atoms, so this is something like a covalent bond, what we're going to be doing is looking at the distance that's in between, so halfway between those two nuclei there. But when we're looking at the size of an atom, we want to think about the effective nuclear charge. And again, as we're moving left to right, the effective nuclear charge increases because we're adding an additional proton to that nucleus. And we're adding an extra electron to balance it out. But since that electron's on the valence shell, it's not getting shielded by any more of those core electrons. So as we go from, again, sodium to magnesium, we go from an effective nuclear charge of 1 to 2. And if we were to continue across to aluminum, +3, silicon, +4, phosphorus, +5. So that's why if we can look at the image here, you'll see the radius of these atoms typically decreases as we go from group 1 all the way across to group 18. And the reason for that is because we're adding electrons to the same valence shell. But now we're increasing the strength of that nucleus, essentially. We're making it more positive. So we're going to have a stronger attraction between those valence electrons and that nucleus. And that's why we're going to see the radius is actually going to shrink a little bit. It's going to condense. And with it, you may be able to notice a few exceptions. So as we're going across the D block, we can see going from molybdenum to technetium, it spikes a little bit, so it goes up. And then even, must be one of the lower groups here, because I'm not seeing anything that disagrees with that. But there is even a few other exceptions in the lower periods here where it does increase a little bit before it going back down. So it's not 100% true, and that's 100% of the time it's going to occur, I should say. So there are a few exceptions, and that's why we're going to refer to it as a trend. So we're thinking about these as periodic trends, just because it's going to be, for the most part, what we observe, but there are a few exceptions to this rule. And I think sometimes thinking about the atomic radius left to right, that one's a little bit confusing, because I think it does naturally make sense as we're adding more protons, as we're adding more electrons, it should increase in size. But again, we always want to think about where those electrons are being added to. And since we're adding them to the same valence shell, but our nucleus is becoming more positive, we're increasing the attraction between those two, and that's why we're seeing the nucleus, or the atomic radius, excuse me, actually decrease as we go from group 1 to group 18. But I think going down the group makes sense, because as we go from the first period down to the seventh, what we're going to see is the size of those atoms is going to increase. And the reason for that is because now, instead of just adding an additional valence electron, now we're going to be adding additional valence shells. So now those electrons are just going to be further and further from the nucleus. And then additionally, when we go down the group, we're not increasing the effective nuclear charge like we are when we're going across the period. So if we think about lithium, sodium, potassium, rubidium, since those are group 1, they're all going to have an effective nuclear charge at +1. But now those valence electrons are getting put into a further and further electron shell. And that's why we're just going to see the atoms ultimately going to expand as we go down the group there. So if we're thinking about the atomic radius of these atoms, the largest atom is going to be francium, so the bottom left. And then the smallest atom would be in the opposite spot. It's going to be in the top right. So the smallest atom is actually going to be helium. And then with this concept of atomic radius, we'll want to keep that in mind when we look at the other trends, because that's going to help explain why we see what we see with the ionization energy and the electron affinity. But in addition to the size of these atoms, we also want to think about the size of the ions. And what we're going to see is that the size of the ions, if it's a metal, they're going to get smaller. So if we look at lithium, and that's what we're looking at in the gray here. So gray represents the atom. The pinkish color is going to be referring to a positive ion. So these are going to be looking at our metals. And then the blue is going to be the ion that is formed from the nonmetals. So in the pink, we're seeing that they're going to be losing electrons. That's why we wind up with like beryllium +2 or potassium +1. Whereas the nonmetals, those blue ones, are negative because they're going to be gaining electrons to fill their valence shell, get that full octet. Whereas the metals just give up all of their valence electrons. So now the shell one within that valence shell becomes the new valence shell. But with these, when we're looking at the size of the ion versus the atom, what we want to do is essentially just think about what's occurring there. So if we think about lithium or sodium, potassium, rubidium, we can see the atom, when it becomes an ion, is going to shrink. And the reason for that is going to be because as a, so for sodium, we saw 11 minus 10 gives us +1. Trying to do this with a mouse, it's a little difficult, so that's why it's just taking me a moment. But we saw with the sodium atom, it's got 11 protons, 10 core electrons, so we wind up with a valence charge, or an effective nuclear charge, excuse me, at +1. When we look at the ion, we still have 11 protons, but if we think about the electron configuration, 1s2, 2s2, 2p6, 3s1. So now when we're looking, that's for the atom. With the ion, though, what we did was we got rid of that valence electron. That's why we got the positive charge. Now we lost that 11th electron, but we still have 11 protons. So that's why we've got a +1. But now if we look at it with the ion, 2s2 and 2p6, these are going to be our new valence electrons. So our only core electrons in the case of a sodium atom would just be those first 2 s electrons. So what we're going to see now is the effective nuclear charge has gone up a whole bunch. Now it's going to be +9. So now we've got a much greater effective nuclear charge, we're going to have a greater attraction between the nucleus and what are considered those valence electrons. And that's why we're going to see with the metals, when they're giving up those electrons, when they're becoming those positive ions, we're always going to see the ion shrink in comparison to the atom, because now we're getting rid of those that original valence shell. And now the new valence shell is going to have a higher effective nuclear charge. It's also just closer to the atom or the nucleus to begin with. So we're going to see a greater attraction there. And that's why with all of these pink ones representing the positive ions, they're all smaller than the gray representing the neutral atom. Okay, and then clear all triangles. Yes. Okay. So then if we do the same thing with, let's pick, let's do sulfur. So as a neutral atom, I shouldn't have erased the entire thing. As a neutral atom, if we just quickly think about the electron configuration, 1s2, 2s2, 2p6, and it's in the third row, so we'll have 3s2. And then if we look at where sulfur is in the periodic table, below oxygen, which means it's going to have 4 of the p electrons, so we'll finish with 3s2, 3p4 there. This p came out really terribly. There we go. Okay, so that's going to be our neutral electron configuration for sulfur. So if we think about the effective nuclear charge on that sulfur atom, we've got 16 protons, because that's the atomic number. That's how many protons we have in the nucleus there. And then for the neutral atom, 3s2 and 3p4 are going to be our valence electrons. So we're thinking about these as our inner electrons. So we've got 2, 4, plus 10, or plus 6 gives us 10 total. And again, for the neutral atom, the effective nuclear charge is just going to be equal to the number of valence electrons it has. But then when we look at the ion, what we're going to see is we no longer have 3p4. We've got 3p6. So when we look at the effective nuclear charge, it doesn't actually change in this case. But what we're going to see now is that they're, because of the additional electrons, that repulsion is going to force them to spread out a little bit. And that's why we're going to see the atomic radius increase in size for these negative ions. Essentially now we've just got extra stuff, but we haven't increased anything about the nucleus. So we're just not going to have a increased attraction between the nucleus and the electrons, but we'll have more of a repulsion between those separate valence electrons, causing them to spread out a little bit more, giving us that larger atomic radius there. Oops, got ahead of myself a little bit by, oops, I guess I didn't realize this is going to stay there the whole time. There, it's clear all drawing there. And then, like I said, with the anions, so the negative ions, so a negative ion is how I remember that one. Because we're not changing anything about the nucleus, we're not increasing the attraction between those valence electrons and the nucleus, but because we've got more of those negative charges now on the outside, there's going to be more of a repulsion between those different electrons in the valence shell, which is going to cause the atom to expand its radius slightly. And then if we go back quickly, with the cation, so the positive ions, I like to think of it as the T is kind of the plus sign in the middle of the word there. Now that we're getting rid of that valence shell, we're increasing the effective nuclear charge. We're going to have a much greater attraction. That's why we see the atom actually shrink with the positive ions. And then just like the atoms, the neutral atoms, we see as we go down the group, the size of these atoms is going to increase. Across the period, you can see they still shrink in terms of left to right for the positive. just because we have the same number of electrons total now in these ions, but we've got more protons as we go left to right. And then the same thing going on here, but you'll notice that there is now sort of a distinction between where we go from positive to negative. So there's a big jump when we go from a positive ion to a negative one there. And then I just used the term ice, or I don't know if I did, but I said they have the same number of electrons at least. That's what's referred to as isoelectronic. So when we're looking at an isoelectronic series, these are going to be, the ions in this case are all isoelectronic because they're all going to have 10 electrons. Sodium has 11 to begin with, but it lost that one to become positive. Magnesium has 12, but it lost 2. Aluminum has 13, so it lost 3. And then similarly on the other side with the nonmetals, these are also going to have 10. It's just they're doing it by gaining an extra 2 for oxygen, going from 8 to 10, or fluorine has 9 originally as an atom, so it gains that 10th one just to become the ion there. But the reason we don't see the trend go all the way across with the radius now with these ions, so the reason we don't see it go fully across left to right is because the effective nuclear charge is going to be greater for the positive metal ions than it will be for the negative nonmetals. And then with the radius, we can kind of use that to sort of explain what we're going to see with ionization energy. So ionization energy is the amount of energy needed to remove an electron from an atom or an ion. And typically what we focus most on is the first ionization energy, so the energy needed to remove that first electron. But we also have ionization energies for the second electron and the third electron. So if you think, if we go back for a second for aluminum, it's losing 3 electrons. So we'd have an ionization energy for that first electron. It would have a different ionization energy to remove that second electron, and it would have a different ionization energy still to remove that third one. But in all cases, we're thinking about the energy needed to remove an electron from an atom or from an ion. And with it, if we look at the ionization energy, we can notice a trend. So with these elements here, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, this is for the third period. So this is actually going horizontally across the periodic table. It's a little bit misleading the way it's written because it kind of makes it look like it's a group, but these are all going to be in the third period. So atomic number 11 through atomic number 18. And you'll notice that as we go from the first ionization energy to the second for sodium, we see a huge jump in the amount of energy needed to remove these electrons. Same thing with magnesium, but now it's from the second to the third electron. Aluminum is from the third to the fourth. And then same thing with silicon, phosphorus, sulfur, chlorine. And then argon has a pretty high ionization energy for everything. Same thing with chlorine. It's actually really difficult to just remove an electron. But the reason we're seeing this is going to be related to the electron configuration, and it's going to be related to the octet that each of the atoms want to reach in terms of their valence electrons. So if we think about sodium, it's got 1 valence electron. It's got that 3s1 electron. And it kind of wants to give up that electron because by giving up that 1 electron, now the second shell becomes its new valence shell, and that shell's already completely filled. So by doing this, by getting rid of that 1 electron, now sodium becomes a stable octet as that positive ion. So now when it's the stable octet, it has no desire to lose another electron. So that's why it's going to take a whole bunch more energy, because if we remove a second electron now from sodium, now we're putting it into a +2 state, but that's not going to be the octet. It's going to have 7 valence electrons now, so it's not something that's really advantageous for that sodium. So that's why we see the big jump in ionization energy from 1 to 2. And it's the same idea for all of these other big jumps. It's just in the case of magnesium now it's got 3s2 as those valence electrons. So it wants to lose both of them, but once it loses those first 2 and obtains that octet, it now doesn't want to lose a third one. So that's why we see a big jump in that energy. Same thing with aluminum. wants to lose those 3 to become the +3 ion, have the same isoelectronic series as these first two. But once it gets to that point, it now doesn't want to lose a 4th one, because now it'll only have 7 valence electrons rather than the 8 that it actually wants. And when we're looking at the periodic table, when we're looking at the trends here, what we can see as we go across is typically it's going to increase. We'll see it a little bit more, that there are a few exceptions. So magnesium to aluminum, we'll talk about why that is. Phosphorus to sulfur actually decreases slightly. But when we're looking at the trend in first ionization energies, so again, this is just the amount of energy needed to remove that first electron. What we're going to see is that it's typically going to decrease going down the periodic table, because the valence electron now is going to be further from that nucleus, but the effective nuclear charge as we go down any one particular group is going to be the same. So if we look at, for instance, beryllium, magnesium, calcium, strontium, and barium, those alkaline earth metals in group 2, they're all going to have an effective nuclear charge of +2. But then when we think about where those valence electrons are, they go from the 2nd shell to the 3rd shell to the 4th shell to the 5th shell to the 6th shell. So if you think about it in terms of one example I like to use in class is just thinking about a water bottle. If I'm holding my water bottle, it's going to take some amount of energy to remove it from my hand. And if I put it across the room, it's going to be easier for somebody to come by and take it then. See the same idea with these electrons. As we go down this group, that electron's getting further from the nucleus. So it's just going to be easier for it to be removed. And that's why we see the first ionization energy decrease as we go down any of these groups. And again, you'll see with the period going left to right, we increase from lithium to beryllium, decrease to boron, increase to nitrogen, have a small decrease to oxygen, and then increase through the rest of the period. And we see something similar in the row below it with sodium through argon, and then even the periods below that too. If you look at going into the 5th period, there we don't really see it too much, just because now we're going to have much larger atoms. The D block is going to be involved too. But with the earlier periods, we see a pretty common trend there, where we increase for these first 2, take a slight dip, increase for the next 3, slight dip, and then increase through the rest of that row there. And that's what we can actually observe here. So this is just going to be representing the ionization energy. So as we go up, it takes more energy to remove that electron versus the atomic number. And you'll notice all these rows, so lithium, sodium, potassium, rubidium, these are going to be the first element in that period. So you can see lithium through sodium is going to be our 2nd row of the periodic table. Sodium through argon is going to be the 3rd. And in the most case, we see it typically increases as we go from the first group through the end of the periodic table till we get to those noble gases. And it makes sense that in each of these periods, the noble gas is going to have the highest ionization energy, because the noble gas already has the most stable configuration by having that stable octet, by having those 8 valence electrons. Only 2 for helium since it's in the first row, but it's kind of the same idea where it's got a full valence shell. So these atoms have no desire to lose an electron. So it's going to be really hard to, relative to the other elements, it's going to be really hard for something to remove an electron from one of these noble gases. And that's going to be why these noble gases are, for the most part, unreactive. They don't really do anything because they're already at that most stable spot. And it doesn't make sense for them to gain an electron or lose an electron, because that's just going to make them higher in energy, and everything wants to go to low energy in the universe. But like I said, there's a few instances where we kind of see a repeating pattern where it goes up, takes a dip, goes up, takes a dip, and then goes up through the rest of the period there. And these are going to be the discontinuities. And the first one we're going to talk about is going to be related to the 2nd and the 3rd electron in each of these periods. So with these ones later on that have the D block, we're kind of skipping over that and just focusing on the electron, the S2 electron, and then the 1p electron, or the p1 electron for each of these shells. So with the second row here, lithium, and then we would have beryllium and boron. The reason we're going to see a slight decrease in ionization energy here is because when we're looking at the different electron shells, when we're looking at the different orbitals, the most stable way we can basically have those is either have them completely empty, have them completely filled, or have them half occupied. So with the second to the third here, think about it again. This is our S2 electron. This is our P1 electron. So the reason it's going to be lower energy to remove the P1 is just because based on the stability, it's easier or it's more favorable to have a empty P block than it is going to be to have a half-filled S block. And then we see the same thing here. It's just in this case, when we're looking at the third row, now it's magnesium and aluminum where we see the dip. And then, like I said, the trends typically for a lot of things tend to get a little bit more messy once we get further down to the periodic table, once we get the D block involved. But it does look like you see a little bit of a dip from, in this case, would be calcium and gallium, or in this case, what is that? Strontium and indium. But it's definitely more noticeable in those earlier periods. And then the other trend we can see is now in the middle of the P block. So if you think about it, that's our P1 electron, P2, and then P3 before it dips down to P4. And I'm just saying P1, P2 rather than like 2P1, 2P2, because we can kind of apply that same thing to all these different energy levels. So it'd be the same thing for 3P to 3,4, 3P3 to 3P4, 4P3 to 4P4, and so on. But again, the reason this is going to occur is because it's better to have a half-filled p orbital, or shell, I guess. Because when we get to this fourth electron in the p block, now we're doubly occupying one of those p orbitals. So there's going to be repulsion between those two electrons. It's going to be a little bit easier then to remove one of them. Whereas in the first three, now we're just placing one of those electrons into, or each one of those electrons into their own electron shell, into their own orbital, excuse me. So there's just not as much of that repulsion there. So we see kind of discontinuities in the trends as we go from the S block to the P block. And we also see it in the middle of that P block there, because now we're starting to doubly occupy those orbitals, which gives us a little bit of the repulsion there. Okay, and then electron affinity now is going to be sort of the, I don't want to say the reverse, because electronegativity is the reverse. The electronegativity is the ability of an atom to attract other electrons. This is going to be related to the energy change when an atom takes on one more electron. So if we look at chlorine, in this case, it accepts one electron. That's why we get it become negative. So we're conserving mass in this case because we got one chlorine on both sides. We're conserving charge because we've got a -1 overall on the right. And then we've got neutral plus -1 on the left. So we conserve the charge there as well. And with this, and then with this electron affinity, typically we're going to see that it's going to become more exothermic as we move to the right, meaning it's typically going to be a more favorable process. But there are a few exceptions to that. So again, and they're going to be, in this case, between groups 1 and 2. So we see it actually becomes more endothermic. That's why these negative. So remember, exothermic, releasing energy, releasing heat. That's why we have these negative numbers, because the system is decreasing in energy. Whereas an endothermic would be absorbing that energy, so it would be positive, it'd be greater than 0. So we see an increase in the endothermic nature of this electron affinity from group 1 to group 2, and the same thing as we go from group 4A to group 5A, or group 14 to group 15, however you want to kind of refer to those. And with the first one, when we're looking at like lithium to beryllium or sodium to magnesium, the reason we see such a large jump, the reason that these become endothermic, is because when we're looking at lithium or sodium gaining one electron, it's got the s orbital, but it's only got one electron in there at that time, so it's able to accept one more into that s orbital. But with beryllium and magnesium, same thing with calcium and strontium, those are going to be less exothermic. In some cases, they'll actually be endothermic, because they already have that s orbital completely filled. So now when they take on that additional electron, now they're going to have to put it into the p orbital. And this electron is going to be just further away from the nucleus. It's going to be repelled by the electrons we already have in that s orbital, which is not good. It's going to make it a less favorable process. And that's typically what we see with endothermic. And then again, and kind of similarly, we're looking at a similar process. It's just now we're looking at the p block. So if we think about it, we've got 3 orbitals in that p block. Each orbital can hold 2 electrons, but we're going to put 1 electron in each of those orbitals before we doubly occupy them. So when we look at carbon to nitrogen, or silicon to phosphorus, germanium to arsenic, tin to antimony, we see that the numbers actually increase. So it becomes less negative, so it becomes more endothermic, or it becomes less exothermic, however you want to think about it. But the reason for this is, again, we're thinking about the orbitals. With carbon or silicon or germanium, we've put the first 2 electrons in their own orbitals, but we still have that 3rd orbital empty, so we can put 1 more electron in there. But now when we get to nitrogen or phosphorus, when we get to this group of the periodic table, now each of those orbitals is already singly occupied. So if a nitrogen or a phosphorus takes on 1 additional electron, it's going to have to go into an orbital that already contains an electron, and there's going to be repulsion there, which is just going to make it a less favorable process. And that's why we're going to see that the electron affinity is actually going to become less exothermic there. And then with the periodic table, again, we've got the groups that kind of give us similar chemical properties as we go up and down any of these columns. But we can also look at the periodic table and see that it's divided into metals and nonmetals. So on the left-hand side, with the exception of hydrogen, are all of our metals. And then with the right-hand side, that's going to be where our nonmetals are located. And with these, we've got different properties between those 2 types of elements. So metals, if you think about it, typically have luster. They're typically shiny. They're malleable and ductile, meaning we can kind of hammer them out into sheets, make them into thin wires and things like that. And with the exception of mercury, let me get the spotlight going again. Oops. There we go. With mercury, that's going to be the only exception in terms of the metals, in terms of the state of matter, I should say, because the metals are all going to be a solid at room temperature, with the exception of mercury, which will be a liquid. And then with these metals, if you think about just wires, conduct electricity, these metals are going to be good conductors, whereas the nonmetals on the right-hand side of the periodic table are going to be the opposite. In some cases, these are going to be gases. So if you think about nitrogen and oxygen, gases that we breathe, same thing with helium. Hydrogen's a gas at room temperature. The noble gases are gases at room temperature. But in some cases, we'll have solids as well. So carbon, if you think about carbon, can be graphite, can be diamonds, depending on exactly how it's arranged. Sulfur, if you've ever seen it, is basically just a yellow, brittle sort of substance that it's almost chalk-like, but it just kind of falls apart really easily. So whereas the metals tend to be malleable, tend to be ductile, we can kind of shape them very easily. The nonmetals are going to be the opposite. If they're gases, obviously that doesn't really apply, but for the elements that are nonmetals and are solids at room temperature, we see them tend to break relatively easily because they will be brittle, and they're not going to be very good conductors compared to the metals there. But just like with the nonmetals, or just like with the metals rather, the nonmetals are going to have one element that'll actually be a liquid at room temperature, and that's going to be bromine. And then you'll notice in the middle here, we've got metalloids. Those are essentially going to kind of be an average or a mixture of metal and non-metal, because they're going to have some properties similar to metals. They're going to have some properties similar to non-metals. So they don't really fit cleanly into one group or the other. So you can kind of use this staircase. You see where it's boldened right here, often referred to just be the staircase of the periodic table. You can kind of use that as the divider. To the left of it, we'll have the metals with the exception of hydrogen. To the right of it, we'll have our non-metals. And then on that staircase, that's where we see the metalloids themselves. And depending on the periodic table you look at, sometimes they also include like polonium and astatine, excuse me, not antimony, SB is antimony. Sometimes they include those as metalloids, so there's some disagreement in the definition of metalloid, but we can basically just assign it to these 7 different elements there. So boron, silicon, germanium, arsenic, antimony, tellurium. But with this, we'll keep these concepts in mind as we move to chapter 8, where we start to look at bonding and Lewis structures and how we can draw and represent covalent compounds and polyatomic ions, things like that.